In this video cast, we'll look at the wave behavior of matter. Last video cast, we said how lots of things, especially really tiny things like electrons and photons of light, actually act more like waves than they do like particles, and yet they act both ways. And so Louis de Broglie, a scientist in the 1900s, said that all matter acts like waves, but it's really only apparent with really small things. In his equation, called the de Broglie equation, said that the wavelength of any piece of matter is equal to Planck's constant divided by mass times its velocity. And you can find this equation on your not-so-good periodic table right here underneath atomic structure, where wavelength is equal to h divided by m times v. And if you forget what these little symbols stand for, remember, just look a little bit to your right, and there you go. There's wavelength, there's m for mass, and v for velocity. So you can see in this equation that mass and wavelength are inversely proportional to one another. The smaller the mass, the bigger the wavelength. The bigger the mass, the smaller the wavelength. And so you can see there's something like a softball that has a pretty large mass compared to something like an electron. Its wavelength is going to be absolutely tiny, and you're not going to see the wave nature of something like a softball. Whereas something like an electron that has a tiny mass is going to have a significant wavelength, and therefore it's going to act more like a wave. So let's look at a mathematical equation that uses this, or a mathematical problem. What is the wavelength of an electron moving with a speed of 5.97 times 10 to the 6th meters per second, and it gives us the mass of the electron, 9 times 10 to the negative 28th grams. So wavelength would be equal to Planck's constant, 6.626 times 10 to the negative 34th joules times seconds, and then divide that by the mass of the electron. And the thing with it is that the joule happens to be a kilogram meter squared per second squared, so we need to take this mass right here and put it into kilograms. So I'm going to write it as 9.11 times 10 to the negative 25th kilograms. Remember, there's 1,000 difference between grams and kilograms. And then I need to multiply that times the velocity that it gave me, which is 5.97 times 10 to the 6th meters per second. Well, when I plug this into my calculator and punch some buttons, I get that the wavelength of the radiation is 1.22 times 10 to the negative 10th, 1.22 times 10 to the negative 10th meters, 1.22 times 10 to the negative 10th meters, or if I want to put this into nanometers, it turns out to be 0.122 nanometers. 0.122 nanometers, and that would be the wavelength. And if I were looking at this in terms of electromagnetic radiation and looking on this diagram, 0.122 nanometers puts me quite a bit smaller than visible light, because visible light is, at its smallest wavelength is about 400. So if I continue to get to be a little bit smaller wavelength, I get up here into the ultraviolet range or so. That's where that's why we can't really see the signature of an electron as light unless it's emitting energy as it moves around. Since small things act as waves and as particles, we're uncertain as to where these wavicles are. I like to call them wavicles because they act not only as a particle, but they also act as a wave. And the new mathematics that had to be developed to deal with this was created by some of the giants in the early 1900s. People like Einstein, like Max Planck, like a gentleman named Erwin Schrödinger that we're going to talk about in a little bit, and a guy named Werner Heisenberg. And Werner Heisenberg came up with this principle called the uncertainty principle, and it doesn't have anything to do with being uncertain in doing chemistry tests, although it certainly could. But what it says is that you cannot know the position, which is symbolized by the letter X, and the momentum, of an electron at the same time. Momentum is mass times velocity, and the triangles here mean change in, and this is equal to or greater than 4 pi, h divided by 4 pi. Anyway, the equation is not super duper important because you have never seen a plug and chug equation question like that on a AP test, but it does, it's worth mentioning because it is uncertain as to the position and the velocity of an electron zooming around the outside of a nucleus. So anyway, this idea of uncertainty, this idea of wave-particle duality, all led to a new treatment mathematically of things that were tiny like electrons. This brought about the new mathematical or the new physics, which is called quantum mechanics. And the gentleman that first put this into a mathematical, a solved mathematical equation was a gentleman named Erwin Schrödinger. And Erwin Schrödinger's equation involved a good amount of something called calculus, which we don't necessarily need to know, but what we do need to know is the solutions, or I guess you could call it the answers to his equation. The problem is his solutions or his answers weren't like numbers. They weren't like the number 6 or something like that. I mean, his answer was not that. His solutions or his answers were actually other equations. And those equations could be graphed. Those equations could be graphed. And it turned out that these equations had to be graphed in 3 dimensions. Had to be graphed in 3 dimensions. And since electrons obviously reside in a 3-dimensional world, right where we are, they were graphed 3-dimensionally to give us something called a probability density or an electron density, telling us probably where the electrons are. Remember, up here Werner Heisenberg said you can't know the position and the momentum of an electron at the same time. Therefore, you can't know where it is and how fast it's going at the same time. And so the way they treated this, and the way Erwin Schrödinger are treating this, was to say, hey, I can statistically say that the electron will more than likely be in this position or in this geographical region, 3-dimensionally at one time. The solutions to the equation gave these things called wave functions. These wave functions are also called orbitals. Each orbital describes a specific distribution of electron density in space, as given by the orbital's probability density. Well, the solutions to Schrödinger's equation brought about things that described where the electrons probably are, called quantum numbers. You can think of them as solutions to the equation that describe where the electrons are. There are 3 different types of quantum numbers that we're going to talk about right now. The first one is called the principal quantum number, and I think we mentioned this in last video cast. The principal quantum number is symbolized by the letter n, the small letter n. And the principal quantum number tells us the energy level. The energy level, how far away from the nucleus an electron is. How far away from the nucleus the electron is. And so if you take a look at this picture right here, I think I showed this one last video cast too, this would be the first energy level, this would be the second energy level, this would be the third. Physically, the further you are away from the nucleus, the higher the principal quantum number. The principal quantum number, letter n, has to be a digit, a whole number digit, like 1, 2, 3, 4, 5. N can equal these possible numbers depending on where the electron is. The larger the number, the further away from the nucleus the electron is. The second quantum number that came about as a result of these equations is called the azimuthal quantum number. Some people call it the sublevel quantum number because azimuthal is hard to say. A-Z-M-U-T-H-A-L. The sublevel quantum number said inside each one of these energy levels there are various substations or sublevels as well. And these sublevels have physical numbers. These numbers go from 0 up to n minus 1. So for example, if you were in energy level 3, n equals 3, the azimuthal quantum number, which is symbolized by the letter L, by the way, script letter L, I forgot to say that. If you were in energy level 3, the sublevel quantum number could have numbers of 0, 1, or 2, depending on where that electron was residing in that energy level. Now, to be more confusing, as chemists like to be, these numbers 0, 1, and 2, also sometimes called the sublevel or azimuthal quantum numbers, sometimes are also illustrated using letters. 0 is analogous to the letter S, 1 is analogous to the letter P, 2 is analogous to the letter D. And if we would happen to have an L equal to 3, which is very possible, it is symbolized by the letter F. S, P, D, and F are 3 wonderful letters for you to know. And the reason that those are important is because these quantum numbers tell you the shape of the orbital and therefore the graphical representation of where the electron probably would be. In other words, what this quantum number does is gives us an equation that when graphed in 3 dimensions gives us a 3-dimensional shape saying this is probably where the electron is. Because remember, that's what the quantum numbers are all describing. The first one says it's this far away from the nucleus, 1, 2, 3, 4, 5. The second one says it's in this particular shape, an S shape, a P shape, or a D shape, and we'll look at those shapes on the next page. The third one, called the magnetic quantum number, actually delves a little bit deeper and says, okay, we know the energy level you're in, we know the shape that you're in. Now what this one says is there is possibly more than one of these orbitals inside of this sublevel. And the magnetic quantum number, symbolized by the letter M, can have values from L, negative L, to positive L. And so if you happen to be in this L equals 2 sublevel, M could have values of negative 2, negative 1, 0, positive 1, or positive 2. Negative 1, 0, positive 1, or positive 2, illustrating that there are 5 different possible sublevels or 5 different orbitals inside of that D or number 2 sublevel. Well, this is getting all confusing, so let's turn to the next page and let's just take a look at a few of these representations of orbitals. Okay, so remember I said that there were 3 different quantum numbers, N, L, and M sub L. N, remember, just tells you how far away from the nucleus the electrons are. L actually tells you the shape of the particular orbital that is a certain distance away from the nucleus. Well, depending on whether the value of L is 0, 1, 2, or 3, it's also designated by a letter. If it is 0, the letter it's designated also by is S. If it's a 1, it's also designated by a P. If it's 2, it's also designated by a D. And if it's 3, it's also designated by an F. Well, S, or L equals 0 orbitals, always have the shape of a sphere. Always have the shape of a sphere. And I have a picture for you of some S orbitals. If I zoom out for just a second, S orbitals look like this. I don't think they're actually pink. But this just shows you that a 1 S orbital, 1 being the N quantum number, how far away from the nucleus you are, and the S sublevel azimuthal quantum number has the shape of a sphere. The 2s, 2 meaning n is equal to 2, and L is equal to 0 in this case because it's an s orbital, would also have the shape of a sphere. And notice as the n quantum number goes up, the sphere size gets bigger, which makes sense because you're further away from the nucleus. Now, notice it also says in this particular, the relative sizes, the 1s and the 2s orbitals for hydrogen. A lot of people will say, yeah, if you look on the periodic table, hydrogen really only has one electron, right? So if it only has one electron, H equals 1 right up here, you see that? How can it have two orbitals? Does the periodic table lie? Is there more than one electron? No, hydrogen has these orbitals, but it doesn't necessarily mean that there are electrons in them. The electron might be right here inside of the 1s orbital, but then if you add energy to it, it might move to the 2s orbital. And remember we said when it moves back and forth from one orbital to the other, if it moves up, you have to put energy in to move it. If it moves back down, it emits energy in the form of light lots of times. So these orbitals all exist in every atom. It's just a matter of that there might not be electrons in some of them. So moving back to this now, s orbitals have the shape of a sphere. P orbitals have the shape of dumbbells. And in this case, L would be equal to 1. And m sub L, remember the third quantum number, could be -1, 0, or +1, indicating that there are 3 different orientations to these dumbbell orbitals. And here are some pictures of these guys. So you can see here, they kind of graphically represented as an electron density area, showing some kind of little dots. I'll zoom in on that just a little bit. You can see that there are like more dots in the middle than on the outside. Remember, this is just like a probability zone of where electrons might be. And you can see that this happens to be on the x-axis of three-dimensional x, y, z axes. This one right here happens to be on the z-axis. And this one right here happens to be on the y-axis. So you can see that they call them the px, pz, and p sub y orbitals. Important thing here for you to know, since it's a lot of information at one time, is that, hey, p orbitals, there's 3 of them. They're shaped like dumbbells. S orbitals, there's 1 of them. They have the shape of a sphere. Okay, that's an important thing to know for right now. We'll get to more specifics later and you'll catch on. Thirdly, d orbitals. Now this is when L is equal to 2. L is equal to 2, which means m sub L could have a value of -2, -1, 0, +1, or +2. Write these guys down because now you can see that there are 1, 2, 3, 4, 5 different possible values for m sub L, meaning that there are 5 different orbitals in the d sublevel. 5 different orbitals in the d sublevel. And you say, well, what shapes are those? I know S's are spheres. Hey, look at this. I got all these pictures for you. S's are spheres, 1, 2, and 3. P's are dumbbells. Here they are. There's the dumbbells once again. Oh, I got another picture of dumbbells so you can see the different pictures. Here's the S's, and then here's the P's, and then, hey, what do the D's look like? Well, there's 5 different D's, and they've got the neatest shapes of all. They look kind of like flower petals. And I'll zoom in on them just a little bit. You can see here's one of the d orbitals, 4 lobes. Here's another one. Here's another one. Here's another one. And this one's my favorite because it's got a Homer Simpson donut right around the middle, right here. Now, what do these mean? These are graphs. These are graphs, just like you have a graph of a line. Well, this happens to be a 3-dimensional graph. And imagine the mathematics that you use to graph something that looks like this. That says this is probably where the electrons are. 90% of the time, the electron in this particular orbital resides inside these green areas right here. And remember, it's difficult to know the position and the momentum of the electron at the same time, and so we can make a probable guess as to where it is, which becomes really important. Like I said, this chapter delves deep into where electrons probably are. So, 1, 2, 3, 4, 5 probability zones for the D or L equals 2 sublevel. Lastly, there are F's. This is when L is equal to 3, and of course M sub L could then equal -3, -2, -1, 0, +1, +2, or +3, which means that there could possibly be 7 different orbitals here. And you say, show me a picture, show me a picture. And unfortunately, I can't right now, but I'll show you one online. I don't have an overhead of that. But they do look similar to the D's, but there are 7 different possible arrangements of those orbitals. They don't show up quite so often, except for in elements with lots and lots of electrons. So to summarize right now, before we go on to the next video cast and delve into this a little bit deeper, and we'll actually rework all of this N, L, and M sub L, let's summarize this. There was this equation called the Schrödinger equation. The Schrödinger equation said, hey, I can graphically solve where electrons probably are. And when I can graphically solve where electrons probably are, I want to graph them. And the graphs turn out to be representations that have specific shapes. Spheres, dumbbells, flower petals, or even wilder flower petals in case of the F's. And in the case of the sphere one, there's only one shape to the sphere. In the case of the dumbbells, there's 3. And in the case of the d orbitals, there's the Homer-Simpson one and 4 others, so there's 5. Maybe you can see a pattern, 1, 3, 5, and 7 different orbitals. And being able to decipher this and determine what are the possible quantum numbers, what are the possible values of quantum numbers, becomes super important, because then it can tell you what the subshells are, what the possible values are, and using the terminology eventually becomes like secondhand nature. This table is given to you in your textbook, and it gives you the values of N, the possible values of L, the subshell possible designation, possible values of M sub L, numbers of orbitals, and the total numbers of orbitals in a shell. This terminology will get easier, and you'll become more used to using it. Good luck with your relationships and quantum numbers.